Alright, so hey everyone, in this video I'm going to be starting chapter 6 for the chemistry final, and I'm going to be covering the types of heat energy. Chapter 6 deals with thermochemistry, which is just heat. This video will not have any formulas, it's purely just definitions because there are a lot of them that you should know, and there are a lot of questions that come relating to these definitions. And the next video will cover the equations. So let's start. The first thing I want to remind everyone of is that there are always two types of reactions when we're talking about heat. You have endothermic reactions and exothermic reactions. Now, of course, endothermic reactions are reactions where you gain energy, and exothermic reactions are ones where you lose energy, and where delta H will stand for heat or energy. So if we just look at how we compare them, I'm going to go through this very quickly because we have covered this a lot in the past. Whenever you have endothermic reactions, the energy rises. In exothermic reactions, the energy falls. In endothermic reactions, the energy of the product is always greater than that of the reactants. The opposite is true for exothermic reactions. When we talk about surroundings, in endothermic reactions, the temperature tends to decrease once the reaction occurs, whereas in exothermic reactions, the temperature will increase. Delta H in endothermic reactions, which is heat, is always greater than 0. In exothermic reactions, it's usually less than 0. And then if we want to talk about examples of each, an endothermic reaction would be something like breaking a bond, melting something, evaporating something, hydrolyzing something. Whereas in exothermic reactions, we just think of the opposites, forming a bond, freezing or condensation, dehydration reactions. And yeah, of course, you can just pause and screenshot at any time if you want to look at this for longer. So now that we've talked about endothermic versus exothermic, I'm going to start talking about the actual different types of heat energy, because the way heat energy works is that it depends on whether it's endothermic or exothermic. So the first one, and this is the most important one, 90% of questions about definitions will come from this one, is the heat of formation. We represent it by HF, the F is for formation, and the definition, which is very, very important, and I will be circling the important parts, is the energy released, so it's always negative, it's always exothermic because we have bonds forming, when 1 mole of a compound forms from its elements in their standard states. So these 4 are all very important. The energy is always released, it's never consumed, it's always 1 mole forming from elements in their standard states. And if we're talking about a pure element, something like oxygen, the heat of formation for it will always be 0. So from this, the basic question that I'm going to be answering is basic question 7. This is where most of the tricks occur. And we are given the heat of the reaction of this reaction over here to be negative 540. And they want the heat of formation. So the best way to solve this is to look at what part of the definition this fulfills. So we know that it's energy released. The energy given to us is negative, so that's correct. We know that it has to be from elements in their standard states. We have hydrogen and fluorine, which are pure elements, and both are gaseous, so these two conditions are correct. However, we don't have 1 mole forming. We have 2 moles of hydrogen fluoride forming. And this is a condition that is not met. And that's what we have to fix in order to find the heat of formation. So to fix this, all we need is to just change this equation so that only 1 mole of hydrogen fluoride forms. So to do that, I'm just going to divide across by 2, where we get half hydrogen gas plus half a mole of fluorine gas. It gives us 1 mole of hydrogen fluoride. Now that we have this and all the conditions are met, all we need to do is just check how the delta H we were given will change. Since we started out here with negative 540 and we divided everything by 2, then all we're going to do is just divide this by 2, and our heat of formation will be negative 270 kilojoules per mole. I also want to look at other ways in which they might trick you for this question, because there are a lot of tricks that come for this. They might, again, just give you the exact same equation, but backwards. They might start with the product, which is wrong. They should always start with the elements, so no. They have to start with the elements. They might make it 1 mole or only, but again, start with the product, which is wrong. We should always start with the pure elements, never with a compound. So, exact same scenario here. The equation might look perfectly accurate. They might start with elements, give you only 1 mole of product, but they will not be standard states. These, for example, say liquid. Hydrogen is not a liquid in its standard state. Hydrogen at STP is a gas, which means this is wrong. They must be in their standard state. They could also, but likely not for this compound, they could do it for another compound. For example, they might say carbon monoxide plus oxygen gives you CO2 and ask if this is a correct equation. It's not correct because you're not starting with an element, you're starting with a compound. You have to start with pure elements. So just keep all of these in mind. Make sure you're paying close attention to the definition whenever they ask you about heat of formation. Moving on, I'm going to be talking about the heat of combustion, which we represent by Hc. And the definition of heat of combustion is, again, the energy released when 1 mole of a compound burns fully. The fully is important in the presence of oxygen because it's released. Once again, it's exothermic and it's less than 0. Again, 1 mole only should burn, and the reaction should be, the reactant should be fully oxidized. So the example I gave over here is of carbon. When we look at these two reactions, both of them involve carbon burning in the presence of oxygen, but this one gives us carbon monoxide and this one gives us carbon dioxide. This one is the one that represents heat of combustion, because here the oxidation is not complete. So to solve this, I'm just using a question I made up. This isn't an actual question in the sheet, but it is important because, once again, they will trick you the same way they do with heat of formation. And the question I'm using is just find the equation for the heat of combustion of methane. So again, if we look at the definition of heat of combustion, we start with 1 mole of the compound burning. So here it should be CH4. It should burn in the presence of oxygen, so plus O2. And any hydrocarbon that burns will always give us carbon dioxide and water. And now it's just a matter of balancing. The one thing you should remember is that when you're done balancing, this should always remain 1. This cannot be more than 1. The definition of heat of combustion is that 1 mole of the compound burns. So if we balance for C, it's balanced. If we balance for water, we put 2 water here. And if we balance for oxygen, we just put 2 oxygen here. And I'm pretty sure that's the correct answer. So again, looking at the ways in which they might try and confuse you with this, they might forget to put only 1 mole of the compound burning. This is wrong. It should be 1 mole burning only. They might swap the equation, which again is wrong. This should always be a reactant and not a product. And they might also give it to you properly, have 1 mole of the reactants on the reactant side, but the products might not be oxidized. They could give you C and H and O on the side. This is wrong. The products should always be oxides and not elements. Like, you should always remember that heat of combustion is not the opposite of the heat of formation. They have nothing to do with each other. One of them deals with bonds forming and one of them deals with oxygen. They're nothing alike. So the products should always be oxides, like carbon dioxide or water. The rest of these I'm only going to be discussing briefly because there isn't much to remember about them. And they come more often in other chapters of this exam, but I just like to mention them here so we can have all our heats conveniently in one place. The third one I'm going to be talking about is the heat of atomization. This heat is always positive. It's represented by H-ATM, and it is the heat required to vaporize 1 mole of an element. So the example I have here is just sodium metal as a solid, and we turn it into a gas. The heat that we use up here is the heat of atomization. Atomization just means turning it into a gas atom. There aren't many questions about this. They tend to just give you the heat of atomization directly, so that's it. The next thing we're going to be talking about is bond energy as well as bond formation energy. These aren't really precise names. We just use these. It's not like heat of atomization where there's a symbol or anything. You just need to know what each one is. Bond energy is the heat consumed when 1 mole of a bond is broken, and bond formation energy is when 1 mole of a bond is formed. And again, if you look back at what we said for endothermic and exothermic, bond energy is always going to be positive. It's an endothermic reaction. And forming a bond is always going to be negative because it's an exothermic reaction. So if we just look at any two equations down here, here we have a chlorine molecule that is bonded to another chlorine molecule. And what we did was we just turned them into two separate molecules on their own. So this is bond enthalpy. We're breaking a bond. In this reaction, we start with hydrogen and chlorine as separate atoms or separate gases, and we combine them together to make HCl. So this is bond formation. And all you need to keep in mind is that if they give you the equation of if they give you the energy for breaking a bond, then the energy for forming the exact same bond will be the opposite. So if they tell you the energy of breaking the CL-Cl bond is 459, then the energy for forming CL-Cl bond is going to be negative 459. And this just makes it easier when you're solving questions. There's not much else to talk about for this. The fifth thing I'm going to be talking about is ionization energy. Ionization energy appears much more in Chapter 7, so I won't be covering any trends or anything here. I'm just going to be going over the definition and what the formula looks like. And ionization energy, which we represent by IEN as a subscript where n is greater than 0, is the energy required to remove 1 mole of electrons from 1 mole of a substance at STP. The equation looks something like this. I do know that this format looks a bit complicated, which is why I'm going to be using some examples down here. And basically, all you need to remember is that in ionization energy, everything is always a gas. We always increase the charge by just 1 at a time, never more than 1 at a time. And there's always only 1 atom involved. So the easiest example is something that we know to be positive, calcium. So if you look at this and how it matches up with the formula, the charge of calcium up here is 0. This is n minus 1. Plus IE1. This is our n, which always has to be greater than 0. So now it says we should have the exact same compound to the power of whatever is down here. So plus 1. And then plus the 1 electron we removed. And like I said, these should always be gaseous. And that's it. And all you need to remember, once again, is that the charge always increases no matter what. So something such as chlorine, which would usually be negative, there's no exceptions here. It's still going to be chlorine plus 1 plus E minus. And it's still going to be gaseous. Something like oxygen, we know that oxygen is usually diatomic and negative. This doesn't apply for ionization energy. Here it's already to the power of plus 1, so it's going to become plus 2, gaseous, plus the missing electron. And this is just the format it always follows. So as long as you remember these first 3 conditions, you should never get ionization energy wrong. The 6th energy I'm going to mention is electron affinity, which is essentially the opposite of ionization energy. We represent it by EA, again to the subscript n, where n is greater than 0. And this is energy released when 1 mole of electrons is added. This is the opposite. Ionization energy is usually endothermic. It's usually positive. This over here is going to be negative because we're releasing energy. So once again, the equation looks like this. Again, it looks complicated, which is why I'm going to be solving a few examples. For example, here we're starting with oxygen, which is already -1, and we're adding 1 electron. So similarly to ionization energy, we're only going to decrease the charge by 1 at a time. We're always going to keep it gaseous, and the electron affinity, because it's released in this format, it's not consumed, it's going to go here. And it's going to be the 2nd electron affinity. Now, if we look at something that's usually positive, just like the ionization energy, we forget about whether it's positive or not here. It's still going to be an A-1, still gaseous, still plus electron affinity. You're usually never going to get anything like this in the exam, but you just need to know the general format of the equation, which is why I'm doing this. Again, we look at magnesium, which is usually, again, to the power of plus 2. Same rule applies. Magnesium -1, gaseous plus electron affinity. And, just remember, everything's always a gas. The charge always decreases, I should have written, by 1. and there's always only one atom involved in the reaction. We never have anything like O2 or Cl2. These just don't happen. It's always one atom only. And the last type of energy I'm going to be talking about is lattice energy, which again, it's discussed in much more detail in other chapters, which is why I'm just going to talk about the definition here. We were presented by LE, standing for lattice energy, and the definition is the heat released when 1 mole of a lattice forms, where a lattice is any ionic solid, such as NaCl, Mg, SO4, anything like this. This involves lattice energy. And all you need to know is that whenever we have a reaction like this, where we get an ionic salt forming, then usually the sum of energy involved in this reaction is always the energy of the first reactant plus the energy of the second reactant plus the lattice energy. We shouldn't ignore it. Again, I will be doing this in much more detail in another video, or somebody else will. This is just the definition for now. And I think that's it for types of energy. I hope it made sense and that you guys understood everything in this video. And good luck in your final. I'm going to see you later. Thank you for watching.